welcome to the new lecture, that is the design to prevent fire and explosion. So up till now in the different modules we have studied different type of fires and explosion. We have classified them. We have find out that what are the causes for those fires, whether it is a positive sense or in a negative sense. Now since we all agreeing upon that these fires and explosion are extremely destructive in nature. So we must design the system through which we can prevent the hazard of fire and explosion. So in this particular chapter, we will discuss all the aspect that how we can prevent the fire and explosion. Though theoretically we know, we all agree upon that if we remove any arm of a fire triangle, then definitely we can extinguish the fire. But sometimes it is not at all feasible. So how we can design the system in such a way that we can prevent the hazard of fire and explosion. So in this particular chapter, we will discuss this type of thing in different modules. So in this particular module, we are going to study the design to prevent the fire explosion systems, how we can design it, different type of inerting, vacuum purging, pressure purging, combined pressure and vacuum purging, vacuum and pressure purging with impure nitrogen, sweep through purging and siphon purging. Now first of all, let us have a discussion about how to prevent the fire and explosion. Usually a twofold strategy is used to limit the potential damage from fires and explosion. One is the prevent the initiation of fire and explosion. Obviously this is one of the foremost requirement. And the second is that minimize the damage after a fire or explosion has occurred. For any fire or combustion explosion to occur, three conditions must be met. Please recall the fire triangle, that fuel, source of ignition and supply of oxygen. And after this, to sustain the fire, net chemical reaction, that obviously in terms of combustion. So if we wish to make the system safer and if we cannot avoid the generation of fire, then you must design the system accordingly. The rule of thumb says if any of three conditions of fire triangle is eliminated, the triangle is broken and it is impossible for a fire or combustion and explosion to result or to sustain. So this is the theoretical aspect. So while designing the prevention methodology for fire and explosion, we must keep this thing in our mind. Now question arises that how we can design the system. So there are 7 broad spectrum through which we can go ahead with designing aspect: inerting, static electricity, controlling static electricity, ventilation, explosion proof equipment and instruments, sprinkler system, and miscellaneous design features for preventing the difference. So we will discuss all the aspect in due course of time in various modules. So let's have first thing, that is inerting. Inerting is a process of adding an inert gas to a combustible mixture to reduce the concentration of oxygen below the limiting oxygen concentration or minimum oxygen concentration, so that the required stoichiometric demand is depleted and flammable mixture or inflammable mixture does not catch fire. The inert gas is usually nitrogen or carbon dioxide, although steam is sometimes used but not in a common fashion. For many gases, the MOC is approximately 10% and for many dust it is approximately 8%. An inerting system is required to maintain an inert atmosphere in the vapor space above the liquid. Suppose I am working here in a pool of say hexane, and just because of its vapor pressure, certain quantity of vapors being generated and just above the pool of liquid surface. So by virtue of my system design, I am not in a position to cordon off oxygen or supply of air. Then inerting is the useful way to minimize the impact of fire hazard. We can introduce certain inert gases so that the minimum oxygen concentration or limiting oxygen concentration is depleted. So ideally this type of system should include an automatic inert gas addition feature to control the oxygen concentration below the limiting oxygen concentration. Now, these control systems should have an analyzer to continuously monitor the oxygen concentration in relationship to the LOC, and a controlled inert gas switch system to add inert gas when the oxygen concentration approaches the limiting oxygen concentration. So that as soon as it approaches to LOC, then it should activate and introduce the inert, so that the whatever oxygen is there, it should come down to the level below the level of limiting oxygen concentration. However, the inerting system consists only a regulator designed to maintain a fixed positive inert pressure in the vapor space. Now, this ensures that inert gas is always flowing out of the vessel rather than air flowing in, so that the impact of air be minimized. The analyzer system, however, results in a significant saving in inert uses without sacrificing safety. Now, thing is that whenever you are introducing inert gas, then definitely certain quantum of money is involved, because ultimately you are going to procure nitrogen or argon, whatever inert gas is being used, and you must have a pumping system through which you can introduce the inert gas to the system. So, if you are having a proper analyzer system, then definitely you need not to bother the continuous supply of inert gas to the system, because ultimately whenever there is a heat system, then if you are having the unnecessary inert gas over there, then it will attract its certain heat value. So, that is why you may have a significant saving if you adopt the analyzer system over there. Now, how we can perform the inerting? This is the big question. So, there are several purging methodology. Purging is one of the way through which you can introduce the inerting material, inerting system. So, there are several purging methods used to initially reduce the oxygen concentration to the low set point. There are 6 different ways through which you can perform these purging operation: vacuum purging, pressure purging, combined vacuum and pressure purging, vacuum and pressure purging with impure nitrogen, sweep through purging, and siphon purging. So, let's have a let's have a look of vacuum purging. Now, vacuum purging is one of the most common inerting procedure for vessels. It's quite simple. Only thing is that it's highly energy intensive. Now, this procedure is not used for large storage vessels, because they are usually not designed for vacuum and usually can withstand a pressure of only a few inches of water. So, if you are willing to adopt this protocol for a large hull or a large vessel, then obviously you can create the vacuum inside, but it will be a costly affair. So, it is usually applicable for a small vessel, small pressure vessels, etc. Now, there are 3 steps involved in vacuum purging. One is drawing a vacuum on the vessel until the desired vacuum is reached. You need to calculate a priori that how much vacuum is desired to have inerting in the particular system. Relieve the vacuum with an inert gas such as nitrogen or a carbon dioxide to atmospheric pressure, and then if you have not achieved the desired result, so by analyzing the LOC or minimum oxygen concentration, then you need to repeat the step number 1 and 2 until the desired oxidant concentration is reached. So, first thing is that suppose you are having the vessel, you need to draw the vacuum, and once it is achieved, then you can introduce, because of the pressure difference, you can easily introduce the inert gas inside. And if it is not, then definitely again you need to repeat the vacuum system to this vessel, and then again you need to introduce the things accordingly till you achieve the minimum oxygen concentration. We can understand this particular aspect through this small plot. Here at the x-axis we are having the time domain, and our y-axis the pressure domain. Now, here the pH is the initial high pressure, this one, and PL is the initial low pressure or a desired vacuum pressure. Why not is the initial oxidant concentration and Y1 is the final target oxidant concentration. So first thing is that you are having certain quantity of oxygen in a system, especially suppose you are willing to have an introduction of inert gas to a vessel. Then initially you are having Y naught concentration of oxygen. Then you reduce the pressure until it reaches to PL, that is the lower pressure limit. Here you maintain the pressure and you introduce the desired oxygen concentration. Suppose you have achieved the desired oxygen concentration by introducing the inert material, and then you raise the pressure so that it can acquire the desired pressure to maintain the reaction mechanism. So here you may have a Y1, that is the final oxygen concentration. And suppose if you are unable to have this LOC requirement, then you need to repeat this system for again and again. So here in this particular plot, the things are repeated for twice. So until it reaches the final desired concentration of oxidant. Now this is you can calculate this through a small mathematical formula, that is concentration after J purge cycle. Suppose in the previous case we have studied 2 purge cycles. Concentration after J purge cycle, vacuum and relief is given by Yj is equal to Y naught into NL upon NH to the power J equal to Y naught PL upon PH to the power J. So you can easily calculate that what will be the final target oxidant concentration under the system in question. So the total moles of inert gas added for each cycle is constant, and you can have a look through this previous figure, in this figure. So for J cycle, the total inert gas is given by delta N, and delta N represents the change in number of moles of nitrogen. Nitrogen in this case is introduced as an inert gas, is equal to J pH minus PL into V upon RGT. T is the temperature of the system, Rg is the universal gas constant, and V is the volume. So by this way you can calculate that how many cycles are required, how many moles are needed, how many moles of inert is needed to inert the system, the pressure system vessel system inside the reactor. Now let us have a look of pressure purging. Now vessel can be pressure purged by addition of inert gas under pressure. Sometimes it performs action like sweep through purging. So after the added gas is diffused throughout the vessel, it is vented to the atmosphere, usually down to atmospheric pressure. So more than one pressure cycle may be necessary to reduce the oxidant content to the desired concentration. Now here again we are having a small plot. Here we are having the high pressure and a low pressure zone. Y naught is the initial concentration of oxidant. So we increase the pressure of the system, and then we introduce the inert gas to it so that it maintains the Y1, that is the concentration of oxidant in the vessel, and then we lower down it again. Then we have the same concentration, and then again we raise the pressure to pH, and then again we introduce the inert system and maintain the Y2 concentration of the oxidant, and then by this way we can have the Y2, that is the number of moles of oxygen in the system. And usually in all systems we used to keep the number of moles of oxygen constant, throughout constant. So in this way we are having 2 pressure purge cycles. Again we are having the mathematical representation for calculating the number of moles after J cycle. Yj is equal to Y naught into NL upon NH to the power J is equal to Y naught PL upon PH to the power J, and the total number of moles of inert nitrogen in the case is added. Delta N nitrogen is equal to J into pH minus PL into V upon RGT. So vessel is initially at say PL and pressurized using the source of pure nitrogen at pH. NL is the total number of moles at atmospheric pressure at low pressure, and then NH the total number of moles under pressure, that is high pressure. So by this way you can calculate the number of moles needed in terms of inert gas to make the pressure inerting. Now, there are so many advantages and disadvantages associated with this pressure purging. Now, one practical advantage of pressure purging versus vacuum purging is that potential of cycle time reduction. Now, the pressurization process is much more rapid compared to the relatively slow process of developing a vacuum. Also, the capacity of a vacuum system decreases significantly as absolute vacuum is decreased. Pressure purging, however, uses more inert gas compared to the vacuum one. So, the best purging process is selected usually based on the cost and performance. So, if you are willing to inert the hydrocarbon piping system, then definitely the pressure purging is most advantageous, because it will be very difficult to have a vacuum purging for a pipeline having a distance of say 1000 kilometer or 500 kilometer. It would be very difficult. So, in some cases both pressure and vacuum purging are available and are used simultaneously to purge a vessel. In that particular case, we need to go ahead with the combined pressure vacuum purging system, because sometimes it is in need of time. So, the computational procedure depends on whether the vessel is first evacuated or pressurized. Now, purging cycle for pressure is the first purge, then purging cycle for evacuate, that is the first purge. So, this is the comparative diagram. Here we are having the pressure first purging, and here we are having the vacuum first purging. Here you are having the initial pressure at say P naught, then it raised up to pH, then introduction of certain quantity of inert material, inert gas, and then the pressure lower down to PL, and then it's a repeated cycle. The same thing here, we are lowering down the pressure to have certain concentration of oxygen, and then it is raised, then again the cycle is repeated to maintain the appropriate level of oxidant within the system. Now, question arises that vacuum, whether we have to choose the vacuum or a pressure, and which one. Now, pressure purging is faster because pressure differentials are greater. So, obviously, if we analyze the things in terms of a cost, in terms of ease of operation, pressure purging is a bit faster. Vacuum purging uses less inert gas than the pressure purging. So, if you are not having a consideration of cost of inert gas, then definitely you can go ahead with the pressure purging, and if it is the consideration, then you may think the option of vacuum purging. So, combination of these two gain benefits of both, especially if the initial cycle is vacuum cycle, so that you can utilize the aspect of pressure differential. Sometimes we may have to use the vacuum and a pressure purging with impure nitrogen. So, previous equations which I have discussed developed for the vacuum and a pressure purging apply to the case of pure nitrogen only. Many of the nitrogen separation processes available today do not provide pure nitrogen. They typically provide the nitrogen in the range of 98% plus minus range. Now, see, the question is that if we go ahead with the highest purity, then the cost of nitrogen production or the cost of inert production would be on the higher side. So, we need to optimize the thing. So, sometimes it is available say 98%, 95% pure, and if it is permissible prior to thinking of the concentration of a nitrogen and prior to thinking about the other impurities present in the nitrogen stream, then it is always advisable to use such kind of nitrogen to reduce the cost of the system. So, assume that the nitrogen contains oxygen with a constant mole fraction of YXY, then Yj is equal to Yj minus 1 PL upon pH plus Y oxygen into 1 minus PL upon pH. So this gives you that what would be the mole concentration of oxygen in due course of time. Now next is the sweep through purging. Now usually it's a very common phenomena, and it's a very beneficial phenomena for keeping the low concentration of oxygen within a vessel. So usually it adds up purge gas into a vessel at one opening and withdraws the mixed gas from the vessel to the atmosphere or scrubber from another opening. It's a commonly used process. When vessel or equipment is not rated for pressure or vacuum, the purge gas is added and withdrawn at atmospheric pressure. Sometimes because of inherent inability, you may not be able to have the vacuum system or a pressurized system within a vessel. Maybe because of the mechanical problem, maybe the vessel is not designed to withstand such a high or a low pressure, then this particular technique is extremely useful. Now usually what we used to do in let's have this this is my vessel. So from one end we used to draw the vacuum, and simultaneously we used to introduce a certain quantity of inert gas over here, and continuously we used to draw the mixed gas from that stream. So once because we have to maintain a certain pressure difference, so we draw the vacuum first stage, then we close it, then we introduce certain quantity of inert gas, and continuously we draw the mixed gas from this front. One time in one phase we are having the advantage, another phase we are having a certain disadvantage. The disadvantage is that whatever mixture is coming out from this, we need to treat this mixture appropriately. It may form an inflammable mixture, so it may create a problem at the exit port. Sometimes it may have some toxic material, then again we need to go for the scrubbing system. So we need to be very careful whenever we are adopting this type of purging scheme. So purging results usually are defined by assuming perfect mixing within the vessel, especially applicable whenever we are designing the sweep through purging. Now we have to maintain the things at a constant temperature and a constant pressure. Under these conditions, the mass or volumetric flow rate of exit stream is equal to the inlet stream, so that we can maintain the properties of the system appropriately. Now here is one of the mathematical relations through which you can analyze the volumetric flow rate. The volumetric quantity of inert gas required to reduce the oxidant concentration from C1 to C2, let us have is QV2, and it is determined using this particular equation. QV2 is equal to V ln C1 minus C2 upon C2 minus C0, where C is the concentration of oxidant within the vessel, C0 is the inlet oxidant concentration, V is the vessel volume, QV is the volumetric flow rate, and T is the time required. Now purging results are defined by assuming perfect mixing within the vessel, constant temperature and a constant pressure. So under these conditions, the mass or a volumetric flow rate for the exit stream is equal to the inlet stream. So these are the certain things we need to keep in mind. Another purging method is the siphon purging. Now sweep through purging process requires large quantity of nitrogen, because you need to fill the entire mass of entire volume of the vessel with the nitrogen. Now this could be expensive when purging a large storage vessel. So siphon purging is used to minimize this type of purging expenses. Now it is a very simple and quite effective. The siphon purging process starts by filling the vessel with a liquid, and sometimes with water or any liquid compatible with the product. Now then the purge gas is subsequently added to the vapor space of the vessel, and liquid is drained from the vessel simultaneously. So it is just like this, that you are having this vessel, you filled it with the liquid, and then you introduce the inert gas, and simultaneously you withdraw the the filled liquid or a water in this case, so that you can inert, because there will be no room for air to entrap, so that the concentration of oxygen would remain low as desired. The volume of purge gas is equal to the volume of the vessel, and the rate of purging is equivalent to the volumetric rate of liquid discharge. So, when using the siphon purging process, it may be desirable to first fill the vessel with a liquid, then use the sweep through purging process to remove oxygen from the residual head space. Now, by using this method, the oxygen concentration is decreased to low concentration with only a small added expense for the additional sweep through purging. So, these things should be in our mind. So, in this particular module, we have discussed a first phase of design to prevent the fire and explosion, and primarily we discussed about the three different purging methodology: vacuum purging, pressure purging, combined vacuum and pressure purging, siphon purging and sweep through purging. So, in the next module, we will discuss the other purging methodology and other methods through which we can prevent the disaster of a fire and explosion. You can always see the various references, those who are enlisted over here, for your further reading. Thank you.